From the moment of his birth, man is involved with machines. Machines can prolong life and then end it abruptly. The study of men and machines, the systematic effort to make their relationship as safe and efficient as possible in a world that grows ever more complex, is one of the newest branches of psychology. It also seems destined to be one of the most important. This field of psychology is known as human engineering, and its pioneers are the engineering psychologists. I'm John Darley. I'm in the control tower at the Idlewild Airport. About 250,000 years ago, man picked up a stone and made an axe like this one. For the next 250,000 years, not very much happened. At least not from the standpoint of engineering psychology, because man continued to work with very simple tools. But since the Industrial Revolution, things have picked up quite a bit. Here, for example, at this busy airfield, we can see how far and how fast we've come. When machines get this complicated, how does man cope with them? It has become the job of the engineering psychologist to find out. The study of man's behavior is the province of psychology. And in today's world, our behavior is very much linked to the machines. In the home, on the roads, at work, we are almost never without a machine of some kind. Therefore, it has become the responsibility of engineering psychologists to study man's behavior with his friend and enemy, the machine. During and after World War II, many psychologists tackled this increasingly complex relationship. Kennedy, Taylor, Morgan, Kapoff, in England, Bartlett and Broadbent, among others. One of the pioneers is Dr. Paul M. Phipps of the University of Michigan.
Engineering psychology thinks of man's relation to machine as a kind of dialogue in which the man and machine exchange information. But this information exchange sometimes breaks down. For example, the housewife, in setting the control on her oven, sometimes sets it too high so that the roast burns. Or the driver, reaching to turn off the windshield wiper, turns off the headlights instead. Engineering psychologists attempt to eliminate such confusion not by changing man's habits, but by changing the machine. They attempt to discover how machines can be designed so that the machine will speak a language which man understands. This means, I believe, that we should study man's habits, determine his natural reactions to stimuli, do experiments such as this simple stimulus-response compatibility study.
Can you hear me all right?
Yes.
This time we're going to test your speed and accuracy of response to signals. In this case, just the center light will come on, and when you see that light, you are to respond just as quickly as you can. All right, are you ready? Your reaction time was 0.17. Your movement time was 0.11. Reset the clock. This time we're going to make it a bit more complicated. Instead of just the center light coming on, any one of the 9 lights may appear. Your task again is to put your finger on the button as quickly as you see the light. All right, are you ready? Your reaction time was 0.33. Your movement time was 0.18.
As you can see, man does best when there are no alternatives. When we increase the number of alternatives in this experiment, man's reactions increase by about 50%. But the task is still a highly compatible one. That is, man's reactions are very natural ones, and he practically never makes an error. Let's see now what happens when we separate the stimulus and the response, and man must control from a distance, as is often the case in the man-machine dialogue.
All right, this time we have a more complicated task. The signal will appear on this panel up here, and you are to respond as before when these buttons down here. Again, touch the appropriate button as soon as the light comes on. Are you ready? Okay. Your reaction time was 0.63. 3, your movement time was 0.17.
The biggest source of confusion in man-machine communication arises when the brain has to translate and interpret information. The next step in our experiment is of this sort. The experimenter rotates the display so that it appears to be seen upside down and in a mirror. Reaction time now may be longer than a second. And you will notice that the subject's movements are uncertain and sometimes made to the wrong target. He can no longer use natural reactions in responding to the stimulus lights. Each step in which we have reduced the compatibility between man and machine has resulted in a fractional increase in the subject's reaction time. At first, this increase of fractions of a second may seem trivial, until one considers that a machine such as an airplane flies hundreds of feet in a city is a matter of life and death. Lack of compatibility means that the pilot makes errors, his reaction time slows down. This is exactly what was happening to some of our pilots in World War II, when engineering psychology first got started in this country. As a matter of fact, it started right here in the cockpits of our planes. We had the cream of American youth preparing for air combat, and yet about 1 in every 100 was being killed in a training accident. Why? It was our job to find out. Pilot's error. Most of these accidents were called on the reports, but we engineering psychologists thought differently. We talked to the pilots, and they called it engineering design error.
Pilot's error, hell. That's an engineering error. He had half a second to flip over to his reserve tank, and it takes 3. Try it once and see.
I can see how it happened. The 2 levers are exactly alike. In an emergency, you don't have time to look, you just grab.
Everybody that flies that aircraft has trouble. They feel for one knob and grab another.
You've never flown the plane before. The whole instrument panel is different. You look around for the airspeed indicator, and it's someplace else.
Obviously, it was not the pilots. Then what was it? We started with the instrument panel. Every indicator on it is important to a pilot, but 6 of them are vital. These are the 6. They tell the pilot his position and his rates of movement in 3-dimensional space. But there was no standard arrangement, and so each time a pilot flew a different type of aircraft, he had to learn a new arrangement of the instruments. In order to find out what arrangement would shorten eye movements, reduce decision time, and save lives, we photographed, measured, and timed actual eye movement patterns of pilots in flight. As a next step, we converted all the data to schematic drawings, compared them, and found that one arrangement required the least amount of eye movements and was clearly superior to all the rest. Today, this arrangement is standard in all military and most civilian aircraft, and the pilots like it. They call it the Sacred 6. But one of the 6 was not so sacred, the standard altimeter. This is what the pilot formerly had to read to find out his altitude. 3 pointers, the long one for hundreds of feet, the broad one for thousands of feet, the small one for 10,000s of feet. At the moment, this one reads 1,500 feet. In a power dive, this is what the pilot sees on his altimeter. Can he read it? Working under Dr. Walter F. Grafter, engineering psychologist at Wright-Patterson Air Force Base, took the altimeter into the laboratory.
We'll start you off in level flight, due south at 20,000 feet. I'll call off course and altitude changes. Whenever the bell rings, you read your altitude. Are you ready?
Roger.
Okay, bank to the right to 225 degrees, and then climb to 30,000 feet.
Roger. $23,500.
Error.
The psychologist knows the correct reading because he has arranged for the bell to ring only at certain predetermined altitudes.
28,900.
Error.
$30,000.
Level out, and then put it into a dive.
22,000. 18, no, it's,
Okay, level out. Pretty tough, isn't it?
Engineering psychologists found that the average pilot took 7 seconds to read all 3 pointers of the conventional altimeter in the laboratory. In the air, of course, where the pilot usually knows his approximate altitude, his reading is considerably faster. In the laboratory, his readings also were frequently in error by 1,000 feet or more. And they were usually wrong in the dangerous direction. That is, the pilot thought he was higher than he actually was. It looked as if we had the answer to many mountaintop crashes and crashes short of the field. Our problem was clear, to find a better way of displaying altitude information. And as we studied the altitude display, we found out more about what the pilot needs to know. This counter, for instance, was easy to read with speed and accuracy. It told the pilot exactly where he was, but it didn't tell him where he'd been, where he was going to be, or how fast his altitude was changing. The search continued. In all, 9 altimeter displays were tested.
We want to try out this new tape-type altimeter. I'll start you out in level flight at 30,000 feet. As soon as you're ready, put the nose down and then level out at 10,000 feet. When the bell rings, call out your altitude.
Roger. 28,000. 26,500. 20,900. 15,000. 10 angels on the nose. This thing really works.
Engineering psychologists found out which designs worked best for man. Design engineers built it. Today, the most modern Air Force planes are equipped with a tape altimeter. It is also available for commercial planes and private pilots. These studies solved some of the problems for our pilots, but other problems remain. It is not only essential that the machine speak clearly to the man must speak just as clearly to the machine. In flight, the right response is a matter of life and death. Here's a scene that has been repeated far too often. When he touched the runway, the pilot started to raise his flaps. Instead, he raised his landing gear. In certain types of aircraft, this accident was tragically frequent. Who was to blame, the man or the machine? The answer again is the machine. And here is the culprit. Identical control knobs, placed side by side, but controlling very different functions. The pilot, touching down at 100 miles an hour, doesn't have time to take his eyes off the runway. And yet, with levers having the same shaped knob placed a few inches apart, it's very easy for him to grasp the wrong one. Without visual cues, what shapes can a man most easily distinguish by feel alone? That was one of the next problems tackled by the engineering psychologists at Wright-Patterson.
We want to find out whether you can tell the difference among these knobs if you can't see them. You can put your blindfold down now and we'll position your hand out here. When I say go, I want you to put your hand down on the knob that is positioned directly under it.
All right.
And when I say stop, I want you to take your hand up.
All right.
Then after each pair, I want you to tell me whether they were the same or different.
All right.
Go. Stop. Go. Stop.
Those were the same.
Go. Stop. Go. Stop.
Those were the same.
Go. Stop. Go. Stop.
Those were different.
As a result of our experiments, we recommended that each control have a different knob shape easily identified by touch. And here are some of the shapes that we recommended. Easily identified by feel without the necessity of using vision. When these shapes were introduced into airplanes, many of the landing accidents were reduced. These experiments, which we have been describing, were some of the early experiments done by the engineering psychologists. In the last 10 years, machines have continued to grow more complicated, and the work of the engineering psychologists more difficult.
Helping man to stay ahead of the machine has become a big job. Let's suppose that a jet plane is coming in for a landing. When the pilot makes a controlled movement, there's a critical time lag before the aircraft responds. If he waits for the response, he'll be too late with his next control movement. He has to be 2 or 3 movements ahead of the plane, or else he's in trouble. Now, how do we keep him out of trouble? To give us the answer, here is Dr. Julian M. Christensen of Wright-Patterson Air Force Base.
First, we have available a greatly expanded and improved engineering technology. But in addition to that, we have learned considerably more about man and his ability to handle these very difficult situations. As an example of the type of research that engineering psychologists are doing to support this effort, we'd like to have you see some work that Dr. Warwick is doing.
When the pilot makes a control movement in his airplane, there's always a lag between his control motion and the response of the aircraft. This means that the pilot must really be a few steps ahead of the aircraft, or else he's in trouble. Now, what we've done here is attempt to simulate a bomber in a landing operation. That is, these computers have in them some of the dynamic characteristics of a bomber under a landing condition. And this little dot right here represents your present altitude. This square represents what your altitude should be if you're going to make a safe landing.
I see. I moved the dot into the square.
Yes, that's quite right. But remember, that little dot's going to be moving up and down. That's because your altitude naturally is changing during landing. And furthermore, of course, you're going to be subjected to some turbulence. So your task is to move that dot down to the square and keep it there. Ready?
Okay.
Fine. Well, how'd you find that?
Pretty tough.
As you can see, this is a very difficult task for our pilot to perform. Now, if we let the computers take some of the burden from him and present only the information he needs in a slightly different form, I think you can see that the job will be much easier, and as a result, the man-machine combination will be much more effective. It's important to note that we haven't changed man in any respect. We have only given him information that is more compatible. This kind of work was started by Birmingham and Taylor at the Naval Research Laboratory many years ago, and what you are seeing here is based on their pioneering efforts.
Okay, now we're going to let the computer do a little bit of the work. You see this horizontal bar of light here on the display? That bar of light represents your predicted altitude. Over at the left-hand edge of the bar of light is your present altitude. At the right-hand edge of the bar of light is your predicted altitude 10 seconds from now. So if you make a mistake on the controls, the computer will tell you about it immediately. Got the picture?
Right.
Good. Okay. We'll try this now. Ready?
Right.
Go.
That's much easier.
Good.
We have seen the computer help one man solve one complex problem. However, in real life, the situation is usually much more complicated. There are many men and many machines dealing with complex interrelationships. Therefore, the engineering psychologist has had to address himself to these types of situations. As an example of work in this area, we'd like to show you some research that's going on at the Laboratory of Aviation Psychology at The Ohio State University, where they are dealing with problems related to the air traffic control situation.
I'm George Briggs, and this is the radar control room of a simulated air traffic control system. Our skies, the airspace above us, are becoming more and more crowded every day. And the man who attempts to control this traffic, the air traffic controller, has a difficult and at times nerve-wracking job to perform. It's something like placing a policeman on the observation deck of the Empire State Building and asking him to direct automobile traffic down on Times Square. In our laboratory, we have students who, instead of flying aircraft, fly these consoles by inserting corrections in the same way a pilot corrects his flight during an approach to the airfield. Also, as is the case in real life, our laboratory air traffic controller can't see the planes he's talking to. And what's worse, the conventional radar display doesn't tell him which plane is which. All he sees on the radar scope is a number of moving blips, that is, dashes of light, and they are identical. The radar display doesn't tell him the altitude of the planes either. He has to remember that, and he has to remember which blip stands for which plane. When the traffic gets heavy, he sometimes forgets. First, we studied the problems that arise in the use of conventional radar displays.
Alpha 1 radar, I'm trying to locate you. Execute a 360-degree turn to the right, over.
Alpha 1 to radar, turning right to 360 degrees.
A sharp course change will show up on the radar scope, and the controller will be able then to locate the plane. But sometimes this leads to even worse trouble.
Alpha 1, what is your altitude, over?
Alpha 1 to radar, altitude 12,200 feet, over.
Bravo 4, what is your altitude, over?
Bravo 4 to control, altitude 12,000, over.
Bravo 4 radar, I have you in conflict with another aircraft. Descend to 10,000 feet.
Descending to 10 Angels, over.
Alpha 1, I have you in conflict with another aircraft. Turn left 30 degrees and hold your altitude, over.
Alpha 1 to radar, banking left, over.
Close calls and sometimes collisions occur because the air traffic controller can handle only a certain amount of information without further assistance from the radar scope. This happens not only in the laboratory, but in real life as well. And there, it costs us a precious commodity, human lives. To get at the principles which operate in this kind of a man-machine system, we have placed our air traffic controller under extreme stress. The two psychologists sitting on either side of the controller are going to measure his performance under an emergency condition which stretches his memory to the utmost. We have overloaded the air traffic control system, that is to say, the skies are jammed with aircraft. And now the radar scope is going dead.
Attention all aircraft, I have lost radar contact. Stand by till further advised. Delta 8. I do not have you on radar. Stand by till further advised. Orbit right until further advised.
Under this kind of a stress, we found that a trained controller could handle efficiently and safely approximately 4 aircraft simultaneously. Today, in this kind of an emergency, the controller at an airport would divert at least some of the aircraft to alternate landing areas. We set as our goal a technique which would shift the burden of memory from the man to the machine. Working under Dr. Fitz, the psychologist provided the engineers with several devices that would tell the controller which plane was which. They were looking for some kind of a code or identifying mark that would make each of the radar blips distinct and individual. After several experiments, they inserted a computer in the system, as we have done now, that would provide a code for each of the aircraft. Without the distinctive coding, he sees this kind of radar display. When the computer is added to the system, he sees this. Every aircraft is identified by a code mark which compares to the hands on a clock. The shape is predetermined. either by a computer or by information broadcast from the plane by radio. Now let us test the controller's emergency responses again.
Attention all aircraft, I have experienced radar failure. Stand by till further advised. Bravo 7, Delta 8. I have lost radar contact. Orbit right until further advised.
Coding has been tested under all sorts of circumstances, and there is no doubt that it contributes to air traffic control, safety, and efficiency. We found that by changing the machine in this way, the capacity of the controller was increased 100%. That is, he could now handle simultaneously 8 aircraft rather than 4. The Air Force is beginning to use coding in their radar approach control centers, and it will become available in the future at civilian airports as well. Of course, coding doesn't solve all the problems in air traffic control. At this moment, engineers and engineering psychologists are seeking more ingenious ways to adapt the mechanisms of air traffic control for an even more compatible relationship between man and machine.
250,000 years separates this axe and this radar system. And the history of engineering psychology spans only the last half-century. Young as it is, this science has already affected our lives and will do so in many more ways, all the way from automobiles to aircraft, from kitchens to space capsules. Engineering psychology stands for man, for the human scale in a world of complex man-machine relations. And it's the hope of every engineering psychologist that his findings will contribute to the mainstream of psychology's efforts to help man understand himself and his world. Focus on Behavior explores the use of computers in studying human mental processes. Can the computer help to formulate theories about human problem solving? The subject, if the machine behaves like man.
This is NET, National Educational Television.